All right, in the last video, we were going over the significance level and the type 1, type 2 errors. So as a review, depending on what significance level alpha you pick, if your p-value is less than alpha, then we're going to reject the null hypothesis. We could be making a type 1 error if the null is true. And I think about this significance alpha is the probability, is the chance of making a type 1 error. If your p-value is bigger than or equal to significance level, we do not reject the null. We could be making a type 2 error if the alternative hypothesis is true. And alpha is related to the chance of making a type 2 error. The probability to make a type 2 error is called the power of a statistical test, which we won't be covering in this class. That would be like a second semester statistics course. So alpha is the chance of making a type 1 error, and it's related to the chance of making a type 2 error. So the idea is you want to decrease alpha. You want to make alpha very small if the type 1 error is bad. If the type 2 error is bad, then you want to increase alpha. Pick alpha to be 5 or 10%. So let's look at a couple examples of what I mean by this, by the type 1 being bad or type 2 being bad. So let's go back to that new blood thinning drug is being tested against the current drug in a double-blind experiment. There are null and alternative hypothesis. The new drug has potentially serious side effects. So if the new drug thins the blood, but it has potentially serious side effects, what should we pick a significance level for? All right, so in that case, if you reject the null and accept the alternative hypothesis, then you might be bringing this new drug onto market. But if it's true that the new drug is the same as the old drug, you should stick with the old drug because the new drug has potentially serious side effects. So this is a type 1 error having a serious side effects, serious issue, excuse me. So a type 1 error would be serious in this case. So you'd want to use a small significance level. Out of these three, 1% is the smallest. Sometimes for, especially with drug testing, pharmaceutical testing, sometimes alpha level of 0.5 or 0.1% are used. So even smaller if there could be some side effects, serious side effects to the new drug. But the point of this is make alpha as small as possible if your type 1 error could have serious consequences. If, on the other hand, the new drug has no real side effects and it costs less than the old drug, you may even argue maybe no side effects and less side effects than the old drug, then you might want to make it more likely to reject the null. So you want to pick a relatively large alpha significance level. So the type 1 error is not at all serious, and in fact the type 2 error might be more serious, at least monetarily, since the new drug is cheaper. You want to make it more likely to reject the null than the alternative. Another way, if we want to reduce the probability of making a type 2 error, not rejecting a false null, you want to increase the sample size. So if we look at an example, to see how large sample size makes it easier to reject the null, if the null is, say, p equals 0.5, imagine you're doing a coin flip experiment, and your p is alternative is more than 0.5, and your p hat is 0.6. If you do a sample size of 10, you're going to get a p-value of in the 30s, 30% or so. Again, here this is with getting 6 out of 10, say, tails. Whereas if you look at the same hypothesis test with a sample size of 100, and you have 60 out of 100, there's only a 2.5% chance of this happening. So if you want to run something like this in StatKey, we should get similar numbers, but not the exact same thing. Go over to StatKey here. We'd want to do a test for a single proportion. Let's see, I can make it fit the window so you guys can see what I'm doing. All right, so here we have go back again to see we're doing a hypothesis test, so it's a test of a single proportion. I want to make sure P is 0.5. And if we take edit data, and here I'm going to make 6 out of 10. We're kind of forcing the sample. We want p hat to be 0.6. Click OK. And let's generate, doing a couple thousand samples. Again, our data down here is 0.6. So to get p-value, you generate your samples, click on the correct tail, left tail, right tail, or two-tail. In this hypothesis test, we're doing the right tail because p is bigger than 0.5. And then make sure here on the bottom, you want to enter your sample results. So it's not 0.8. I'm going to click that and make this 0.6. And here we go. In this case, we get a p-value of close to 40%. You would never reject the null hypothesis with this type of p-value. Whereas if we get the same hypothesis test, p equals 0.5, p is greater than 0.5, and p hat being 0.6, let's edit that data and change this to 60 out of 100. So we still have 0.6 as my p hat. Null hypothesis should still say 0.5. Generate a couple thousand samples. Click on your right tail. Change this bottom number down here instead of 0.59. Make it 0.6. Click OK. And here we get a p-value of 0.022. And this is in the, you would reject the null if your alpha was, say, 5%. And then you would not reject the null if alpha is 1%, but it's definitely still in the range of rejecting. So same hypothesis, null alternative, same sample data, different sample size will decrease chance of making a type 2 error. Because if you have a big sample size, you're more likely to decrease. So a larger sample size makes it much easier to reject the null. If you have a big sample, a small change in the outcome makes it more likely to reject the null. So like I said, with small sample sizes, even large differences or effects may not be statistically significant, and type 2 errors are common. So if you have a small sample, that's what you want to kind of put a warning in or something into your study saying we have a small sample size, so we want to be wary of these type 2 errors. On the flip side, if you take a very large sample size, even a very small difference or effect can be statistically significant. So here, let's talk about the statistical versus practical significance. If you have a weight loss program that has a sample size of 10,000 people for randomized experiment. So huge sample size, you get 10,000 people, say split them into 2 groups of 5,000 each to check 2 different weight loss programs or supplements or exercise routines, whatever it may be. And suppose a difference in the average weight loss is only 0.5 pounds between the 2 groups. But since the sample sizes are so huge, that would usually be found to be statistically significant. That there's a difference in weight loss. But suppose that experiment lasted for a year, is the loss of a half a pound practically significant? So these two, could be very different, statistically significant because there's a huge sample size and there is a difference. But in practicality, you'd say, well, half a pound is not really practically significant. So a statistically significant result is not always practically significant, and that especially comes into play with large sample sizes. So that's one of those, when I teach this class, a lot of students say, well, I always need a bigger sample size. And generally, bigger is better for sample size, but there does come a point where your sample size could be, I don't say too big, but that could lead to statistically significant results that are not practical. Okay, so just a quick summary. I like this section because this is getting to the gray area of hypothesis tests. They're very, very important. They give us a lot of information, but there is a lot of conditions. The conclusions based off p-values are not perfect. Type 1 and type 2 errors can happen, and they often do happen, especially if you're just doing one test. Your significance level alpha is the probability of all tests that will yield significant results just by chance. And oftentimes only the statistically significant results get published, which is a problem. File drawer effect. Replication of results is important. Larger sample sizes make it easier to get statistically significant results. And for more details, I linked a paper here talking about kind of a statement on p-values. They could be overdone. And we'll finish this video series with a comic strip.